Assalamu alaikum warahmatullahi wabarakatuh. Bismillahirrahmanirrahim. My name is Bilal Ahmed Ramzan and my presentation partner is Mr. Imran Qayyum. Now today's we will talk about industrial gases. There are many gases which are used in industries, but here we will discuss only three gases which are mainly used in industries. Number 1 hydrogen, number 2 oxygen, number 3 nitrogen. These gases are used for different raw materials for the manufacturing of other chemicals. First of all, we discuss about hydrogen. It is an important gas which is used for the raw material of different chemicals and petroleum industries. Hydrogen is solid and liquid gas. The liquid gas is most profitable. Now we start the manufacturing of hydrogen. Hydrogen is almost derived from carbonaceous material like primarily hydrocarbons and water. These carbonaceous material or water is decomposed by application of energy, which may be electrical, chemical or thermal. There are different methods exist for the manufacturing of hydrogen, which we will discuss one by one. Number 1 is electrolytic method. The electrolytic process produces high purity hydrogen and consists of passing direct current through an aqueous solution of alkali and decomposing the water according to the following reaction. This is an endothermic reaction. The second one is hydrogen production in microbial electrical cell. In this cell, the fermentation of plant occurs. Plant-based fermentation produces acetic acid. Bacteria consume acetic acid, releasing electrons, protons, and carbon dioxide. Electrons are used as power source. Carbon dioxide goes an anode and proton goes to the cathode, where electron converts protons into hydrogen, which is pure gas, which is also used as vehicle fuel. The third one is steam hydrocarbon reforming process. In this process, a mixture of steam reacts with hydrocarbons in the presence of catalyst at high temperature, which is shown in following reaction. In this process, light hydrocarbons are used like methane. Now we discuss reforming reaction. The following reaction is called reforming reaction. It is highly endothermic reaction. It operates at high temperature under low pressure. For this reaction, excess steam is required. Now we talk about process flow diagram for the production of hydrogen. For the production of hydrogen, mostly propane is used as feed. As the shown in diagram, desulfurizing feed is introduced with process steam and propane vapors are formed. Propane vapor mixed with steam is reformed over nickel catalyst and about 815 degrees Celsius temperature in alloy tubes in combustion furnace. Then these gases, hydrogen, carbon monoxide and carbon dioxide, are cooled about 370 degrees Celsius and partial pressure of water increased by addition of steam, then passed over an iron oxide catalyst in the first stage carbon monoxide converter, where 90 to 95% of the carbon monoxide is converted to carbon dioxide for more. Now hydrogen manufacture partial oxidation process rank next to steam hydrocarbon process in the amount of hydrogen made. In this process, use natural gas, refinery gas or other hydrocarbon gases mixture as feedstock. The most important method for the production of hydrogen is partial oxidation process. The oxidation is a non-catalytic partial combustion of the hydrocarbon feed with oxygen in the presence of steam. The following reactions are used for the oxidation process. This process is highly exothermic process. For efficient operation, heat recovery using waste heat boilers is important. The other method is coal gasification. Coal is a source of hydrogen which increasing the importance in future. Although coal was used in water gas and produced gas plants for the manufacturing of hydrogen and carbon monoxide mixture. Comparison for four main process for hydrogen manufacturing. Number 1, steam reforming. In this process 70% hydrogen is obtained. Number 2, coal gasification. In this process 60 to 65% hydrogen is obtained. Number 3, electrolysis. In this process 32% hydrogen is obtained. 4, thermochemical decomposition. In this process about 55% hydrogen is obtained. By comparison, we conclude the most useful method is steam reforming. Now we talk about the purification of hydrogen. In the purification process, the removal of carbon monoxide, carbon dioxide and hydrogen sulfide is important. Carbon monoxide is removed by water gas shift reaction. Carbon dioxide and hydrogen sulfide is removed by monodiethanol amine. The following reactions are used for the purification process. Stripping with steam at 90 to 120 degrees Celsius capable of reducing carbon dioxide concentrated to 0.015 volume.
Absorption purification. Number 1, fixed bed absorption. There are different kinds of absorption. In absorption purification, fixed bed absorption can remove CO2, H2O, CH4, C2H6, CO, AR and N2 impurities. Number 2, thermal and pressure swing absorption. Number 3, thermal absorption. Number 4, pressure swing absorption. Now I will tell you the advantages of pressure swing absorption over thermal absorption. It operates at short cycle. It reduces vessel sizes and absorbent requirements. It is used to purify typical hydrogen stream to less than 1 to 2 ppm total impurities. Cryogenic liquid purification. In this process, the gases are liquefied at very low temperature. In cryogenic liquid purification, highly purity obtained, for example 99.99%. In this process, temperature is almost minus 180 degrees Celsius. Now, the next industrial gas is oxygen gas. Manufacturing of oxygen. There are different methods for manufacturing of oxygen. Number 1, cryogenic process. Number 2, pressure swing absorption process. Number 3, electrolysis of water. Number 4, by chemical reaction in which oxygen is freed from a chemical compound. Now I will explain you the flow sheet for oxygen and nitrogen manufacturing. The air is compressed to about 94 psi in a multi-stage compressor. It then passes through a water-cooled cooler to condense any water vapor, and the condensed water is removed in a water separator. The air passes through a molecular sheet absorber. The absorber contains zeolite and silica gel type absorbent, which trap the carbon dioxide, heavier hydrocarbons and any remaining traces of water vapor. The absorber is cleaned to remove the trapped impurities. This usually requires two absorbers operating in parallel so that one can continue to process the airflow while the other one is flushed. The pre-treated airstream is split. A small portion of the air is diverted through a compressor where its pressure is boosted. It is then cooled and allowed to expand to nearly atmospheric pressure. This expansion rapidly cools the air, which is injected into the cryogenic section to provide the required cool temperature for operation. The main stream of air passes through one side of a pair of plate fin heat exchangers operating in series, while very cold oxygen and nitrogen from the cryogenic section pass through the other side. The incoming airstream is cooled while the oxygen and nitrogen are warm. In some operations, the air may be cooled by passing it through an expansion valve instead of the second heat exchanger. The airstream, now part liquid and part gas, enters the base of the high pressure fractionating column. As the air works its way up the column, it loses additional heat. The oxygen continues to liquefy, forming an oxygen-rich mixture in the bottom of the column, while most of the nitrogen and argon flow to the top as vapor. The liquid oxygen mixture, called the crude liquid oxygen, is drawn out of the bottom of the lower fractionating column and is cooled further in the subcooler. Part of this steam is allowed to expand to nearly atmospheric pressure and is fed into the low pressure fractionating column. As the crude liquid oxygen works its way down the column, most of the remaining nitrogen and argon separate, leaving 99% pure oxygen at the bottom of the column. Meanwhile, the nitrogen argon vapor from the top of the high pressure column is cooled further in the subcooler. The mixed vapor is allowed to expand to nearly atmospheric pressure and is fed into the top of the low pressure fractionating column. The nitrogen, which has lowest boiling point, turns to gas fast and flow out the top of the column as 99.995% pure nitrogen. Higher oxygen purity. If higher purity is needed, one or more additional fractionating column may be added in conjunction with the low pressure column to further refine the oxygen product. If the oxygen is to be liquefied, then this process is done with low pressure fractionating column. Uses of oxygen. It is one of the life-sustaining elements on Earth and it is needed by all animals. Oxygen and acetylene are combusted together to provide very high temperatures needed for welding and metal cutting. When oxygen is cooled below -297 degrees Fahrenheit, -183 degrees Celsius, it becomes a pale blue liquid that is used as a rocket fuel. It is used in blast furnace to make steel and is an important component in the production of many synthetic chemicals including ammonia, alcohol and various plastics.